So if we talk about the reliability, first of all, of course, we need to investigate the conditions for best linear and biased estimators. And we discussed previous time, what does it mean? Which assumptions should we hold if we want to obtain blue estimates? And of course, building on this, we shall develop a test of hypothesis about our slope. If we talk about the simple regression, or maybe about several slopes, if we talk about the multiple regression, the idea behind how can we check the reliability is the same in simple and in multiple regression. In both cases, we used probability theory and we used hypothesis testing. So this is our plan for today. We talk about the probability distribution of our estimates, about our coefficients, testing hypothesis, and after this, we talk about some extensions. We talk about the transformation of our variables and how to work with the dummy variable if we want, for example, include in our regression analysis not only continuous variable, but also we work with the categorical variable. We also work with the binary variables. And how can we interpret the coefficients associated with the binary dummy variable in the regression analysis. But this will be at the end of our lecture. But first, let's start with the interval estimation of the coefficients. So what is the problem with the point estimation? A point estimate, of course, might provide us with the best guess of some population value. But of course, this point estimates itself doesn't have any information about how close the estimate is to the real population parameter or the true population parameter, We discussed this because we work with a sample, but our main hypothesis, our main research question is, of course, about the population. For example, let's say that we have a random sample of workers, and we want to answer on the question about the job training influence and wage level. This is our general example from the previous lectures. So let's say that we get that job training grants increase hourly wage by around 6%. But this conclusion, this result, we get from the sample. And our question is, how are we to know whether or not this is close to the effect in the population of workers who could have been trained? So, for example, if we obtain all the population of workers and run the same regression that we did in the sample, should we obtain again that the job training grants increase hourly wage by the 60%, by 6%, sorry. So we need to answer on the question when we want to decide if the relationship exists and this relationship is significant, is the same task as we want to decide whether or not some slope parameter in the regression to predict our dependent variable from our independent variable is different from 0. So if this slope is different from 0, it means that the factor, X factor, has some influence on our dependent variable, in other words. So, and if the slope is 0, then our dependent variable doesn't tend to change if our independent variable changes, and vice versa, So the problem is that we don't know the population value. And because of this, we cannot know how close our estimate for some particular sample. And however, of course, we need to solve this task. And we can make some statements involving probability theory, involving statistics, and we can estimate interval and use this interval estimation for our further analysis to make some predictions. Okay, so when we start to talk about the interval estimation, of course, our first step, except the coefficient itself, also we need to obtain some variability parameter. Or in other words, we need to obtain sampling variance. Because you remember that our estimated parameters, let's name the like beta 0 with the hat and beta 1, of course, they vary from sample to sample. Yeah. And for example, if we obtain these parameters from one sample, then we change the sample, but use the same population, we obtain other parameters. And understanding this variability is a real key to assessing the reliability and sampling precision of an estimator. Because, of course, we want to make some conclusion about the precision of these estimators. And our goal, our main goal, is to estimate the parameters close to the true parameters. And the variance of an estimator measures how much the estimates can vary from sample to sample. So the variance of the random variable is the average of the squared distance between the possible values of the random variable and its mean. So let's use this definition to find the difference for variable x, and let's write variable y through also the difference between observed value and the mean value. If we use this notation, so the formula of our variance of our slope will look like this. So in the numerator, you can see the variance of the error term, and in the denominator, you see the difference between the squared difference between the observed value of our x and the mean value of the x. So the standard error is just the root square of the variance. And the variance of intercept looks pretty much at the variance of the slope, but the difference is that we adjust for the number of observations in the denominator, and also we add in the numerator the squared observed values of our x. Why it's important to take a look very clearly at the variance? Because again, yeah, variance is a measure of how much the estimates can change from sample to sample. And if we want to obtain precise coefficients, we need to understand which terms influence on our variance. So let's start with the first term, with the variance of our error term. How can it influence on our result? So the variance of the random error reflects the dispersion of the values y about the expected value. This is obvious, yeah? And so if we obtain the high value of this variance, it means that our dispersion becomes higher and greater, yeah? And it means that the greater it's the uncertainty in the statistical model and the larger the variances of the least squares estimators. And you can notice that this expression, the expression of the variance of the error term, appears in each of the expressions. So in the slope and also in the intercept, and it reflects the dispersion of the values y about the expected value. So when the variance of the error term is larger, so the information we have about our coefficients is less precise. And this makes sense since, of course, more variation, in the unobservables, in the error term, this is our unobservables, affecting our dependent variable and make it more difficult to obtain precise estimates of our coefficients. So if we have some choice, or we prefer to obtain the variance of the error term as small as possible. The second term from these formulas, this is the difference between observed x and mean x. So, and on the other hand, if we talk about the independent variables, we prefer for more variability in the independent variable, because the variability in the x increases, so the variance of our slope decreases, because this term is in the denominator and help us to decrease the variance of our coefficient. So the more the spread out our independent variable, the values of this independent variable, the larger the sum of the squares. And the larger the sum of the squares, I mean this difference here, the smaller the conditional variance of the least squares estimators, and the more precisely we can estimate the unknown parameters. So what is the idea? How can we visualize this and why it works like this? For example, you have two samples. In one sample, from the one sample, you can obtain this scattergram, and from the second one, you can visualize this with this scattergram and try to fit the line. Yeah. So the intuition behind this assumption about the variability in X demonstrated exactly here. So figure B is a data scatter in which the values of X are widely spread out along the X-axis. Yeah. And in this figure, you can see that data, let's say, looks like they are bunched. Yeah. So let's say that you have a task and you task to draw a fitting line by hand, for example. Which data scatter plot do you prefer? A or B? So I think that it's pretty clear that data in figure B could help you to do a better job if you want to draw a linear regression, sample linear. Yeah, because from this graph, the least squares line must fall more accurate. And because of this, the more spread out in the sample of your independent variable you have, the easier is to find the relationship between the dependent and independent variable, because this line reflects the relationship between dependent and independent variable. So because of this, if you have a choice, of course, you need to choose the case when you have more x values, more variability in x. Yeah, but it's very pity. But in most cases, we unfortunately don't have any choice, and we use data that we can find, and that's all. Okay, but this is the discussion about the how can we increase the how can we estimate the coefficient more precisely. Next term. And next term in the formula of variance of our coefficient is the sample size. Let's name this like n. So the sample size, of course, appears in each of the variances, because each of the variance consists of some observations. Yeah. And also you can, let's again take a look at the formula. Also, you can find that number of observations appears explicitly in the formula of variance of the intercept here. Yeah. So let's return to our slide. So the larger the sample size, the smaller the variances of the least squares estimators. And of course, again, if we have a choice, we prefer to use more sample data than less in our analysis. And also, the sum of squares term gets larger as the number of observations increase, because each of these terms in the sum is positive or equals 0, at least. So let's make a conclusion that if we have more observations and if we have an option to increase the sample size, in this case, we have a chance to obtain the variance of the slope gets smaller. And the last term in the formula, this term appears only in the variance of the intercept. This is the squared sum of x, and the larger this term, the larger the variance of the least squares estimator. So let's summarize. This is the formula that we will use when we want to obtain the variance of our slope. And the formula for the variance of the intercept you can find on the previous slide. So how can we manipulate with our data, for example, with our sample, if we want to decrease the variability in the coefficient? What can we do if we have a choice again? Yeah. The higher variance of our dependent variable, or our error term, the higher the sampling variance. And the lower the variance of our independent variable, the higher the sampling variance. And also, as we increase the number of observations, the denominator gets large, while the numerator is fixed, yeah, because it doesn't depend on the number of observations. So the sample variance shrinks to 0. And after this, we can calculate the variance of our beta. But we have one question. This is the variance of the error term. So the question is, how can we estimate this term? Because many times we discuss that we don't know anything about the error term. So if we don't know anything about the error term, of course, we don't know anything about the variance of this error term. How can we obtain, in this case, this term? And how can we calculate the variance of our parameter? What do you think? What instead of error term could we use? Because we need to estimate the variance of the coefficients anyway. So we need to maybe to change the variance of the error term by some other indicator. What is the error variance? Okay, do you remember the difference between the residual and the error? Could we use here the residual, the variance of the residuals? Okay. Let's first of all, okay, in this case, I recall you that if we don't know the the value of the true error variance, of course, in some extremely rare case, we know the variance of the error term when we work with the population, yeah? But I don't think that during our course, or for example, when you will conduct your own research product, you have such opportunity to work with the whole population. So in most cases, in absolutely most cases, you work just with the sample. So when we work with the sample, the kind of analog of the error term is the residuals. Yeah. And we can estimate this term from the sample using the residual variance. I hope that you remember this formula, how can we obtain the residuals? And of course, errors are not the same as the residuals, because the residuals, this is the difference between the observed values and between our estimated values of dependent variable, right? And the errors, this is the difference between some unobserved true values of the population and the observed values. So we don't know how to calculate errors. And because of this, if we want to use, instead of variance of the error term, we can use this formula, but we need to adjust this formula by the number of observations minus 2. Why we should do this? Because in other case, the estimator of the difference between observed values and the estimated values of y is biased. Is biased because it doesn't account for several restrictions that must be satisfied by ordinal least squares residuals. if you remember the first order conditions, we discussed that first order conditions restrict the residuals. And one way to view this restriction is that if we know this term of the residuals, we can always get the other two residuals by using the restrictions implied by the first order conditions. So when we want to obtain the variance of the residuals, we need to adjust for degrees of freedom. Yeah, you remember, I hope that you remember what does it mean, degrees of freedom, from your statistic course. And after this, we can obtain the variance of the residuals, and we can plug in this variance in the formula of the variance of our coefficient. You will, in a week, not this week, but in a week, you will practice how to do this by hands. So you will calculate the point estimates, and then you will calculate the variance of this point estimates and test some hypotheses. So maybe if you don't clearly understand now how to obtain these values, you will have practice on this point, okay? So after we have all the terms, we can estimate the variances of the least squares estimators, beta 1 and beta 0. And also you can estimate the covariance between them. And the square roots of these estimated variances are the standard errors. We use the abbreviation like as E of beta 1 and beta 0 again. So the standard errors of these coefficients are also measures of the sampling variability of the least squares estimates of our parameters in repeated samples. Yeah. So the standard errors we will use, these standard errors we will use in the hypothesis testing, and when we will construct the confidence intervals for our point estimates. So previously, we didn't discuss what type of distribution the least square estimators have. So now we can obtain the mean value, yeah, the expected value of our estimated parameter. Also, we know how to calculate the variance of this parameter. And the last question that we need to define before we want to test any hypothesis and construct any confidence intervals, the last question that we need to define is what is the distribution beta 1 has. So we need to know something about this question mark. And we have different type of distribution, yeah? You know, we have t-distribution, normal distribution, exponential, uniform, and other kinds of distribution. Of course, we talk about the continuous distribution, yeah? So do you have any guess which one we obtain? What the form of the distribution our coefficients have? I think that you have some guess, but let me say, for example, if you have a large sample, if you have a really large sample, what type of distribution what the form of the distribution of the least squares estimators? What do you think?
Maybe normal.
Yeah, maybe normal, because we have the central limit theorem, yeah? And what this theorem states. So if we make the assumption that the random errors are normally distributed, the first assumption, with the mean zero and the variance, then the conditional probability distribution of the least squares estimators are also normal. So we need to make two assumptions about the error term, that this error term are normally distributed, these errors are normally distributed, and also that we treat with our independent variables with x as given. We discussed this previous time. And then the least squares estimators are normally distributed. And this works in large samples. But next question is, for example, we don't have a large sample. Yeah. What should we do in this case? What type of distribution should we assume before we need to test any hypothesis? And the second question is large distribution. This is good, but what does it mean? So what does it mean sufficiently large number of observations that we obtain in our sample? And the question is, how large is sufficiently large? And the answer that really we don't know. The answer that there is no specific number. For example, we can't say that if we have 100 of observation, this is sufficiently large. But because we have a lot of factors that influence the distribution. For example, our random errors look like skewed or symmetric or smooth, and what the x values looks like. So the meaning of sufficiently large will change from problem to problem, and from sample to sample, and from our research question to our research question. But of course, result is frequently invoked in regression analysis, and we have some assumptions. Even if we work with the small samples, we can hold these assumptions to assume that we have approximately normal distribution. What are the assumptions? Of course, linearity, random sample, variation in x, zero conditional mean of the errors, homoscedasticity. All these assumptions are the same as in the large samples. But also we need to add one more assumption in small samples. And this assumption is that our errors are conditionally normal distributed. This is one more assumption for the small samples. So you can check this. For example, you can obtain your residuals, and you can check this assumption about the normality of errors by looking at the residuals. For example, by looking at the residual scattergram. And also, if you have some problems with the normality, you can use variable transformation, and this transformation can help to come closer to the normality. We did this during the previous seminar, yeah. We use log transformation, and these help us to change the distribution, log normal distribution, and our variable looks more like normally distributed variable after this transformation. And also some small reminder that in really large samples, the assumption about the normality is weak. Yeah. So after we obtain point estimates of the coefficient, the variance of these estimates, after we assume the form of the distribution of these variables, now we are ready to find the interval estimation and also test some hypotheses about the statistical significance of our coefficients. So point estimates of the unknown population parameters in the simple linear regression model represent some inference about the regression function describing this relationship between variables. And interval estimation, what I hope that you remember, yeah, this from previous course, that proposes some range of values in which you can find the true parameter of your coefficient. So you need to provide this range, this interval of values, and give a sense of what the parameter value might be, and also give a sense for the precision with which you have obtained this interval and make your conclusion. So also such intervals are also called like confidence intervals. Yeah, you remember this. And hypothesis tests are some procedures for comparing your guess about the regression parameter to the parameter that you obtain from your model, from a sample. Yeah. And of course, the procedures for hypothesis testing and interval estimation depend on assumption of the conditional normality, yeah, of the least squares estimators in general. So if this assumption doesn't hold, yeah, again, you need to work with sufficiently large sample. So how you can use the statistical inference of your regression? You have three options. The first one, this is just a point estimation. And the second one, we discussed this during the previous lectures, yeah. And now we want to discuss these 2 points, point 2 and point 3. We want to discuss hypothesis testing, consider the sampling distribution of a test statistic to test hypothesis about our coefficients with some significance level. And also we want to discuss the interval estimation. And of course, if we want to test the hypothesis and if we want to obtain interval estimation, we need more information than just the mean value and the variance of the sampling distribution of our slope. So we need to know the full shape of sampling distribution, and use some steps. So the first step, we need to state the null hypothesis and alternative hypothesis. Then we need to choose the significance level. After this, compute the value of our test statistic and determine the p-value. Then compare this p-value with the significance level and make our conclusion about the null hypothesis and the significance of our result. And also at the last step, we need to interpret our result of the hypothesis step and make our final conclusion about the significance. All the steps look pretty similar like you did when you want to compare your sample mean with your population mean, yeah, they looks the same. But now we talk about our beta parameters. So what is null hypothesis? In many cases, in economic and business decision problems, these problems require some judgment, yeah? So judgment about whether or not some parameter equals specific value or greater than specific value, or for example, less than specific value. So we need to test some hypothesis. In our case, when we want to test the hypothesis that our coefficient is significant, at the beginning of this lecture, I told you that significance of some coefficient means that if this coefficient equals 0 or not. So if this coefficient equals 0, it means that this coefficient associated with our independent variable, doesn't have any influence on our dependent variable. So the null hypothesis is the straw man that we want to knock down. And in most cases, of course, we assume in the null hypothesis that there is no any relationship. Or in our case, it means that our coefficient equals 0. And also the null hypothesis assumes that whatever you are trying to prove didn't happen. And of course, alternative hypothesis means that you will obtain some effect. And again, yeah, you should remember that this hypothesis about the population parameters, they are not about the ordinary squares estimates based on the sample, yeah? We use just these estimates based on the sample to check the hypothesis about the population. After you formulate the null hypothesis, you can use the t-statistic, yeah, and use this formula to find this t-statistic. What should you find? You need to obtain estimated value from your regression, this coefficient, yeah, and also some hypothesis value. Hypothesis means, for example, 0, if you check that your coefficient equals or not equal 0. And also, you need to divide this by the standard error of the estimated. So this is the standard formula of t-statistic. And why should we use t-statistic here? Because you remember, yeah, that instead of standard error of the estimator, yeah, instead of standard error, we use standard error of our residuals. So we use sample, and because we use sample, we use the standardized coefficient follows t-distribution with n minus 2 degrees of freedom. So in general, degrees of freedom here equals number of observations minus the number of the parameters, including your intercept. So for example, in simple regression model, minus 2 because you have only the intercept and only one slope. For example, if in your model you will have more than 2 parameters, for example, you will have one intercept and let's say 2 independent variables, so 2 slopes, it means that the degrees of freedom here will be number of observations minus 3. I hope that this is clear. If we continue our example with the null hypothesis, where we test that our coefficient equals 0, it means statistically significant or not. So we can rewrite this formula like this one, yeah. So we run t-test to examine the statistical significance of the variable. And we know that t-distribution we can use here. And also, when we obtain this t-statistic, we can find t-critical value and find the rejection regions. So also, I want to know that instead of 0 here, yeah, instead of the 0 in the null hypothesis and alternative hypothesis, you can plug in here some specific value. For example, your coefficient equals 1.3, and you want to use one side hypothesis test, and for example, check if your coefficient could be less or greater than some specific value, let's say specific equals 2 or 1.7. So is it clear that in the null hypothesis you can check any specific values, not only 0. 0, this is about the significance. Okay, so after we obtain t-statistic, we can use rejection region to check if our result is statistically significant or not. But before this, of course, we need to choose the significance level. And in this graph, you can see that two shaded areas that equidistant from the null hypothesis value, and the total probability of these equidistant areas equals 0.05. So 5% significance level, yeah? And we call these shaded areas the critical region for a two-tailed test. We have two-tailed test here. And these critical regions define how far away our sample statistic must be from the null hypothesis value before we can say that it's unusual enough to reject the null hypothesis. And if the value fall within this critical region, one of these, for example, yeah, this indicates that it's statistically significant at the 5% significance level. So the rejection region consists of some values that are really unlikely obtain and that have low probability of occurring when the null hypothesis is true. This is the general idea behind the this approach of hypothesis testing. And if this probability is really very, very low, it means that the alternative hypothesis could be true, yeah? And the values of test statistic will tend to be unusually large, for example, or unusually small. And this definition of large and small, these terms are determined by choosing the significance level. So we compare this with the significance level. And for this purpose, we use p-value, yeah, as usual, as usual in the testing hypothesis. And p-value here is some probability value, some number, yeah, of seeing a test statistic at least this extreme if the null hypothesis were true. So in other words, p-value can tell us how likely it's that your data would have occurred by random chance. And in most cases, we use 5% significance level, or in other case, we can say 1 time in 20 is regarded as unusual chance. Or, for example, if we want to choose more strong significance level, more stronger threshold, let's say, we can use 1% significance level or even less. And if we use 1% significance level, we say that we regarded the chance as unusual if we obtain the result that is less than 1 time in 100, less than this value. And also, what is the significance level? What does it mean, significance level? This is also some probability, but probability of what? This is the question for you. Da, Miroslav?
Yes, well, it is the probability of rejecting the null hypothesis when it is true.
Absolutely right. Yeah, this is the probability of yeah, and Arozhan, you're also right. Rejecting the null hypothesis when this null hypothesis is true. Because of this, of course, we want to obtain our results with the small significance level. So in this case, we have really strong probability that we obtain the correct results. But it's very important that you should remember we have 5% significance level and we have 95 in this case. We have 95% of probability that alternative hypothesis it doesn't mean, I should say that it doesn't mean that with the 95% probability that the alternative hypothesis is true, yeah? Because significance level is unrelated to the truth or falsity of the alternative hypothesis. Significance level is only about the null hypothesis. And also, you should know that you cannot accept the null hypothesis. You can only reject the null hypothesis or fail to reject this. And because of this, when you will interpret your results, you can use such phrases like you provide support for some conclusion, or for example, you give evidence for some conclusion. So you should be very clearly and you should carefully write your conclusions or state your conclusions, because every time you should remember that there exists maybe very, very small, but anyway, there exists some probability, some chance that the null hypothesis was correct, but you reject this null hypothesis. Maybe even if this chance equals less than 0.1%. Yes? So please avoid some phrase that you're sure or something like this. Okay, so after you calculate t-statistic, point estimate, standard errors, you can construct the confidence intervals. Usually we will use 95% confidence intervals, and these 95% confidence intervals constructed by the default in Stata and in some other softwares. But the question, this formula looks pretty similar as the confidence intervals for the mean values. Yeah. You did this during the statistic course, but here, instead of mean value, you obtain your estimated parameter, your slope, for example. This t-statistic you can obtain from the critical from the statistical table with the critical values of t distribution, and the standard error of this coefficient obtained from the formula that we've just discussed today. So the question is, let's say that we have the sample with more than 300 of observations. And we want to construct 95% confidence interval. Which value of t statistic here should we plug in this formula? Do you remember the critical value of t statistic? We will very often use this value in our calculations. Do you remember? So 1.96, yeah? You can find this value of t statistic from the statistical tables of t distribution. I hope that you remember this. Okay, anyway, let's move to our extensions. So that's what the discussion about the interval estimation and testing hypothesis. But also, previous time during these seminars, you should discuss that sometimes we want to incorporate non-linearities in our regression. Sometimes we need to do this when we, for example, want to transform our distribution, and we can use log transformation. So log transformation is a data transformation method in which it replaces each variable of our x with the log of this variable. When our original continuous, I want to stress that we're talking only about the continuous data when we talk about the log distribution, yeah? When these continuous data don't follow the bell curve, we can log transform this data to make it as normal as possible. Because in this case, statistical analysis and our conclusions from this data become more valid, yeah, according to the assumption about the normality. And very important that before you use log transformation, you should check that your original data has to follow or approximately follow a log normal distribution. Otherwise, the log transformation won't work. And we can, for example, use log transformation in several ways. We can regress a log transformed dependent variable on x. And in this case, our beta parameter approximates % increase in dependent variable associated with 1 unit increase in x. Or we can regress without any log transformation our dependent variable on log transformed independent variable. And in this case, our slope parameter approximates increase in dependent variable associated with a % increase in x. And of course, we can transform both sides of our equation. We can transform independent variable and we can transform dependent variable. So let's take a look. Let's take a look at this table, not this table. Let's take a look at this table. Here you can find all the combinations of our models if we want to use log transformation. You can use this table at first when you learn how to interpret the coefficients, because in the last column you can see here some hints how can you interpret your beta parameters. For example, let's take a look at this model. When you use dependent variable with the log transformation, yeah, you check the distribution of y and you decided to log transform this variable, but your independent variable is the original variable without any transformation. In this case, you can interpret your result not like in the level model without any log transformation. Yeah, in the level model here, how can we interpret our beta coefficient, our beta parameter? We say that 1 unit increase in x change our independent variable by some value of beta, yeah, some value of beta coefficient. But when we have this type of functional form in the log level model, we interpret our beta coefficient with some correction. We say that 1 unit increase in x affects our dependent variable by this beta coefficient multiplied by 100%. And this is the difference in the interpretation. So please remember about this table. And when you will learn how to interpret different models with the log transformation, please take a look here and have some practice. You will do this also during the seminars. Now let's return. Why should we use log transformation? Again, these transformations are often recommended for skewed data, and it's very convenient then when we use log transformation logarithm with the base, with the natural base, with the e, it means that we can interpret our change as the percentage change. And this is really very convenient in our tasks. And for purpose of business analysis, it's really a great advantage that small changes in the natural logarithm of variables are directly interpretable as the percentage change to a very close approximation. So this is exactly what you can find here in this table, that we can interpret small changes as approximately percentage change in our model. So you can see here in this model, and in the last one. Okay, so and also one more case when we can use log transformation. So because in some cases we want to linearize our model. For example, if you remember from the microeconomics Cobb-Douglas production function, this function looks like this. So our dependent variable here is the output, so the quantity of some output, and the L here is the quantity of labor, so some positive parameter, and here is the quantity of capital. So here you can see that the original model implies that your independent variable has a multiplicative relationship with your dependent variable. And usually we work with the additive relationship, yeah? So if we use log transformation, if we take the logarithm for both sides, for this side, for the left side, and log use logs for the right side, we can transform our original model like this. And now we can just use ordinal least squares method and obtain the coefficient that associated. Here's alpha and 1 minus alpha, this coefficient, to estimate the effects of the capital and the labor on our dependent variable on the output. So now we can straightforward estimate and we can straightforward use linear regression model. And here, if we didn't change our original model of Cobb-Douglas, it will be really problematic to use ordinal least squares method. So it's very convenient to use properties of logarithms, and you remember that the product of the logarithm of products of two factors equals the sum of logarithms of these factors. This is general property of the logarithms. And this is really a very useful property for us. So we can linearize some models. Okay, now let's have some practice. Let's take a look at this output, data output from the regression analysis. So here you can see that the dependent variable is a logarithm of wage, and education, this is independent variable, so we have a simple linear regression here. And let's choose which type of model do we have here among 4 of these. Which one?
Maybe log level.
Yeah, we have the third one here from this table, log level model. So because our dependent variable with the logarithm and our independent variable in levels. And in this case, when we will interpret the coefficient, we need to correct them by 100%. So let's practice how can we do this. But first of all, let's take a look at this row. You can see that this is the point estimate, and this is the standard error associated with this point estimate. And today we discuss how can we calculate this term, how can we calculate this term, how can we calculate this term. You can find all this information on the slides of today's lecture, and also how can you construct confidence intervals. Yeah. So why do we need to check these terms? First of all, we need to, before we start our interpretation, first of all, we need to understand if this coefficient is statistically significant. What do you think? If you want to make some conclusion about the statistical significance of the coefficient, you can take a look, for example, at the p-value. You can take a look at the confidence intervals, and also you can take a look at the t-statistic. So you have several options. How can you conclude something about the significance of this coefficient? What do you think about our slope? At the 5% significance level, what do you conclude?
We need to reject our null hypothesis.
Yeah, we need to reject our null hypothesis. Why? Because of which
Because our p-value is smaller than any alpha, that is why we can reject.
Yeah, Elizabeth, you're right. So if we take a look at the p-value is less than the significance level, even 1% significance level. Yeah, even less than 1% significance level. And also we can take a look at the confidence interval. If this confidence interval includes 0, it means that the coefficient is not statistically significant. In our case, we have a range of positive numbers without the 0 here. And so again, we can conclude that our coefficient is statistically significant. And also we can take a look at the t-statistic, because if you remember, in one of the approach that we can use, we can compare our t-statistic with our t-critical value. And we discussed today that t-critical value at 5% significance level, when we have enough observations, our sample large enough, as in our case, we can compare this t-statistic with the t-critical value equals 1.96. Yeah, you can check this. So again, we can make, of course, the same conclusion that our coefficient is statistically significant due to the t-statistic, p-value, and confidence intervals. Okay, and now let's interpret this value, 0.08 after rounding. How can we interpret? What does it mean? So it means that this is the slope. Yeah, so the slope estimate that one more. I should say firstly that education we measured in the years, and wage, original variable wage is measured in the dollars per hour, but here is the logarithm of wage. So the unit of measurement of education years, and we can say that one more year, it's better to say one more year of education increases hourly wage by 8.2 or 8.3 after rounding percents on average. Is it clear why 8.3%?
Yes.
Okay. If it's not clear, please again take a look at this table. Okay. Next, sometimes in our models you will see not a continuous variable like this. Yeah. Sometimes you will see that in our model we want to include, and in most cases, of course, we want to include some categorical, or let's start with the binary variable. So here we have the same sample with the wage, but we want to change our independent variable, and now we want to find some effect of, let's say, gender effect on the wage. This is rather popular task when you want to make some conclusion, for example, about the is there any difference between the female and male in level of wage between the female and males. So this is the question about maybe some inequality, yeah, gender inequality. So when we work with the binary variable, it's equivalent to performing difference of means analysis. So here you obtain the coefficient, and this coefficient again is statistically significant at 5% and even 1% significance level. Here is the coefficient minus 2.5. And female variable means this variable has two categories. Category 1, if respondent is a female and this variable equals 0, if respondent is a male. So you need to learn that base category in categorical and in binary variables, we need to find base category. And base category in these types of variables are the category that equals 0. So why do we need to define this base category? Because our interpretation of these variables, our interpretation of the, it's better to say, of the coefficient associated with this variable, also in the context of the base category. So the best way to interpret this parameter in regression is to consider one at a time the two possible cases, females equals 1 or females equals 0. So in this case, this coefficient is the difference between mean values of women's wage and mean values of male's wage, if we talk about the simple regression model, yeah? So let's try to visualize this example. Because our x variable could consist only with two values, 0 and 1, we can visualize this variable like this. So we can see only some values here when the x variable equals 0, and some observations when the variable equals 1. So here's female and here is male. Of course, we can try to run the regression, the linear regression here, and maybe it looks not very beautiful, but anyway, you can see that based on these results, we see that the predicted wage for females is about 5%, or not percent, yeah, it's about 5, yeah. And if we compare with the predicted value, predicted because we fit a line, a regression line here, and the predicted value for males is around 7, yeah, like this. So our preliminary conclusion from this graph that we see the statistically significant difference between the level of wage for males and females. And also, if you run the mean analysis, the description analysis before the regression, you can see the same results. You can see that wage, mean value of the wage for males equals 7, and mean value of wage for females equals 4.6. So let's return to our regression analysis. So the question is, after all this discussion, how can we interpret this coefficient? And the main difference, if we compare how can we interpret the result of continuous variables with the result of binary variables, that we need to compare two groups. So based on these regression results, females have wage value that are 2.5 dollars per hour less than males. So anytime when you will interpret coefficient associated with the binary or dummy variable or even categorical variable more than these two categories, every time please remember that you should specify your base category. In our case, base category is males, and you need to interpret this coefficient comparing with the base category.
Excuse me, I have a question.
Yeah, of course.
How can we understand which of two categories is base?
You should check which category equals 0, because your binary variable, your dummy variable, always should be coded like one category should equal 1 and the other one should equal 0. You remember, yeah, what means the binary variable?
Yes,
so,
yes.
Yeah, when you find the category that equals 0, it will be your base category.
Okay,
and all
understood.
your, and all your interpretation should be you should compare your coefficient within two groups. Yeah. So in this case, we compare the wage of females, and we find that this wage is statistically significant lower by this value, than the wage of males. And also we can prove this with this graph. You can see the same interpretation. Here, because this is the regression line, and you can see that for females, the mean value, the predicted value, is less than for males. And this difference is statistically significant. So that's all for today. Do you have any questions? If you're confused a little bit about the interpretation, I want to assure you that you will practice during the seminars. So don't worry about this. Some other questions? Okay,